I want to talk about something that might seem a little daunting at first: neural networks. But trust me, the fundamental ideas are really quite elegant. Think of it like building with Legos, but instead of plastic bricks, we're building with mathematical relationships. It all starts with the perceptron. Imagine a single light switch. It takes an input, let's say a signal, and decides whether to turn on or turn off based on a certain threshold. That's essentially what a perceptron does. It takes some inputs, applies a simple calculation, and spits out a single output. Now, the real power comes from stacking these perceptrons together, creating layers. The first layer takes the raw data and transforms it. The second layer takes the output of the first layer and transforms it further, and so on. This stacking is what we call a full network. It's like building a complex system by adding more and more processing steps. But just building a network isn't enough. We need to train it, to teach it what to learn. And that's where things like loss functions and gradient descent come in. Imagine you're trying to shoot an arrow at a target. You release the arrow, it curves off course, and you adjust your aim based on where it landed. That's gradient descent. We calculate the loss, how far off our prediction is from the correct answer, and then we adjust the network's internal parameters to minimize that loss. It's a constant process of trial and error, guided by mathematics. Now, a crucial thing to understand is the risk of overfitting. Let's say you're memorizing the answers to a specific quiz. You'll ace that particular quiz, but if you're asked a slightly different question, you'll struggle. Overfitting is when a network learns the training data too well. It memorizes the noise and peculiarities instead of learning the underlying patterns. Conversely, there's underfitting, a model that's just too simple, unable to capture the complexities of the data. The trick is to find the right balance. To help us avoid overfitting, we use a validation set. We split our data into 3 parts: training, validation, and test. The training set is used to teach the network. The validation set is used to monitor performance during training, essentially a checkpoint. If the network starts performing poorly on the validation set, it's a sign that overfitting is occurring, and we need to stop training or adjust our approach. And that brings us to the next stage. We're moving beyond single inputs and exploring how to handle sequences of data. Think about processing text. Words are ordered. They have relationships to each other. Or consider audio. The order of the sound waves matters. The upcoming lecture will focus on models designed to process this sequential information. We'll delve into ideas that can capture these relationships. You'll learn about models capable of understanding the order in which things happen. Specifically, we'll start to investigate techniques used to build models that can learn from sequences, models that are able to identify patterns within data that changes over time. And within that, we'll be looking at things like RNNs, recurrent neural networks, which are specifically designed to handle sequential data. These are clever networks that remember information from previous steps in the sequence, allowing them to make more informed decisions. Then, we'll move on to even more sophisticated concepts like transformers and attention mechanisms. Think about how you focus your attention on the most important parts of a sentence when you're reading. Attention mechanisms allow a network to do something similar, weighing the importance of different parts of a sequence. So, that's the foundation. Don't be intimidated by the terminology. The core ideas are about building intelligent systems that can learn from data. It's a powerful approach, and with each step, we'll be unlocking the ability to build truly sophisticated systems. Let's keep building.